In this lecture, we'll talk about Cauchy's integral formula and some consequences of it. The Cauchy integral formula is really consequence of Cauchy's integral theorem, and the way we introduced analytic functions, this is really the basic property, namely that the contour integral around any curve, at least if you're in a simply connected domain where you have an analytic function defined all over, every such contour integral will be zero. That is the Cauchy integral theorem, and it's a basic property of analytic functions. So now, suppose that we have this situation, and here is our simply connected domain, which we can call omega, and then we have a closed contour inside here, and we suppose it's oriented in this direction as usual, and then we have a point in here which we call Z0. Then Cauchy's integral theorem states that if f is analytic in all of omega, then the value of f at Z0 can be written as 1 over 2 pi I times the integral over this contour gamma of f of w divided by w minus Z0, like this. So one of the immediate conclusions of this integral formula is that you see that the value of any analytic function at any interior point here, that is any point inside the contour, is completely determined by the values of the function on the contour itself, which again shows us that the concept of analyticity is a very strong restriction on the function. So how do you prove this? Well, let's start with the right-hand side then. 1 over 2 pi I over gamma f of w divided by w minus Z0 dw. Well, the trick here now is that you should add and subtract a certain term here now. So the term you add is 1 over 2 pi I, and then you have almost the same integral. It's only that you have not f of w, but f of Z0 up here. But of course, then you have to subtract the same term. And if I write minus this together with this can be written as one integral in the following way then. You get f of w minus f of Z0 divided by w minus Z0, and then dw then. And the point here is now that once we have a constant up here, I mean Z0 does not depend on the variable integration. You might as well put f of Z0 in front here now. So you can write it at f of Z0 times the integral 1 over 2 pi, or 1 over 2 pi times the integral over gamma of dw divided by w minus Z0. And as we know, we can deform this this integral to just say a circle around this point here now. That's the Cauchy integral theorem. And then this becomes a standard integral which we have already computed. And the value of this integral is just 2 pi I. And so this integral cancels out against this factor. And we see that this whole term here is just equal to f of Z0 then, which is what we really wanted to prove. So what remains to see now is why must this integral vanish? Well, the idea here is again that you can modify the contour here. Instead of integrating around this contour, you can integrate around a small circle around the point Z0, which we can call gamma epsilon, where epsilon is the radius of the circle then. So this can then be written as 1 over 2 pi I times the integral over gamma epsilon of f of w minus f of z0 and divided by w minus z0 dw. And so why should this integral be 0 then? Once we've seen that, we have proved the Cauchy's integral formula then. Well, the reason is now that what you integrate over here is actually a continuous function in this whole domain. Because if outside the point Z0, we have assumed f to be C1, for example, then. So there's no problem. But at the point Z0 itself, you see that this converges to the derivative of f at the point Z0. And if you just originally the function is of course not defined at the point Z0, but if we define the value at that point to be just the derivative, then this obviously gives a continuous extension of the function, and we have a continuous function in all of omega actually. And then we see that then this function of course must be bounded also. So if you just choose some fixed set around this point Z0, you can say that you have an upper bound on the integrand here. It will be, the absolute value of this must be less than m then. And the length of the curve depends of course on epsilon. But if you take the absolute value here now, you see that you get 1 over 2 pi, and then you get this constant m, which dominates the integrand, and then you get the length of this curve, which is then 2 pi epsilon. And when epsilon, now you can let epsilon tends to 0 because there's no restriction for that. So then you see that this will go to 0. And since this is actually independent of epsilon, you see that it must have been 0 from the beginning then. So this is how we can prove the Cauchy integral formula. And this formula has a lot of very interesting consequences. One first observation we can make is now that if you consider this now to be a function of z, so we don't consider a fixed point, but we let z vary here now, like this. Then this expression will be infinitely differentiable with respect to z. This, of course, takes a little work or some theory from real analysis that you can really differentiate a integral depending on some parameter under the integral sign. So instead of differentiating this expression, you might as well just differentiate with respect to z in here. And it's not difficult to prove that all the conditions for this are satisfied in this situation. So I won't go into those details. Just observe that to differentiate this function is just to differentiate here with respect to z. So for example, you see that the first derivative here now will be equal to, and if you compute the derivative of in here, it will be just taking the square here. So here is gamma and here is gamma. And once you have this formula, you can again go on differentiating, and you get a general formula for the kth derivative of the function here now. So this will be equal to k factorial divided by 2 pi I times the integral over gamma of f of w divided by w minus z to the power k plus 1, and then dw. And since you can do this as many times as you like, according to the theory, then the function will be infinitely differentiable. And also you can use this formula to get some estimates on the function. So if we now apply this, for example, to a circle with radius r. So here we have a circle around some point and with radius r. Then we see that the kth derivative at the point z here now can be written as, well, we have first this factor, k factorial, and then divided by 2 pi I, and then we have this circle parameterized in this way, and then we have f of w and divided by w minus z to the power k plus 1 dw. So if now this circle is the one which has its center at the point z, then you see that if we take the absolute value here now of the kth derivative, then that must be less than or equal to, first of all, this k factorial, and then we have the factor 2 pi here now. And then if you take the absolute value of this integral by the triangle inequality for the integral, you can put the absolute sign in here. And if we suppose now that f of w is bounded by m, say on this circle, then we get an m here, and then we get this denominator, which will, if the radius of the circle is r, then this will just be r down here, because, well, the distance from any point w on the circle to z is just r. So we get r to the power k plus 1, and then we get the length of the arc also, which is 2 pi r. So we arrive at the estimate here now that the kth derivative at z absolute is less than the m here now, which is the you can say it's the maximum of f on the circle here now, and then times k factorial, and then divided by a to the power k. So these estimates, they are very interesting in their own right, but they also lead to rather spectacular consequences. So, for example, let us now consider a function f of z, which is entire and bounded. So entire means that it's analytic in the whole plane, and bounded means that there is a constant, say m, such that f is, the absolute value of f is less than m in the whole plane then. What can we say about such a function? Well, from these estimates you can easily see that now that f must actually be equal to a constant. Why? Because you see, in this formula here now, in this estimate, once f is entire, you can choose r as large as you like. But m is fixed, and k, you consider just one k at a time then. So this means that by choosing r arbitrarily large, so to speak, you see that this must be arbitrarily small. So actually you conclude that all the derivatives at all points must be 0. And this is what is called the Liouville theorem. It states that a bounded entire analytic function must be constant. And this again has a very interesting consequence here now if you apply it to the fundamental theorem of algebra. Remember, the fundamental theorem of algebra states that every polynomial, every complex polynomial must have a root. So if P of Z is a complex polynomial, then there is a Z naught, a complex number Z naught, such that P of Z naught is equal to 0. This is the fundamental theorem of algebra. So how do you prove it using Liouville? Well, the idea to prove the fundamental theorem of algebra is that you consider the function 1 over P of Z. And then you see that if P of Z does not have any 0, then this will be an entire analytic function. And if you can prove that if you know that it's an entire analytic function, and in addition if we can prove that it is bounded, then Liouville's theorem will tell us that it must be a constant. Of course, the constants are accepted from the fundamental theorem of algebra, but every polynomial of degree at least 1 will then have a 0 then. So how do you prove that this is bounded? Well, we observe now that we can write the polynomial as an times z to the n plus an minus 1 times z to the power n minus 1 and so on, plus a1 z plus a0 then. And then if you know, and an is different from 0 of course, because there's always a highest coefficient here which is different from 0, and this is in our case an. Then if you divide by z to the n, you see that you get an, and then you get terms like a n minus 1 times 1 over z, and so on here now, down to a1 times z over n, 1 over z to the power n minus 1, and a0 times 1 over z to the n. And if you now let z tend to infinity here now, you see that all these terms will go to 0. And so the conclusion is that this quotient will go to the limit an, which is different from 0. So you see that the limit of, when z tends to infinity, of p of z divided by z to the n is equal to an, which is different from 0. But now the the definition of this limit will tell you then that there must be hence a number rho. There exists a number rho such that if absolute value of Z is larger than or say equal to rho, then it follows that P of Z divided by Z to the n absolute must be larger than absolute value of n divided by 2. Actually, you simply define you use the definition of limit here with epsilon equal to this number here now, absolute value of n divided by 2. And then the definition of a limit will produce this number rho for you. But once we have this, you see that you can now invert that and conclude that the function f of Z the function f of Z, which was 1 over p, then you will can estimate this function now by inverting this and say that this is then less than or equal to 2 divided by Z absolute to power n times an absolute. And of course then, if you consider the region where absolute value of Z is larger than rho, then this will be less than the constant 2 divided by rho to the power n times absolute value of an. So here we see now that outside the circle with center at the origin and radius rho, the function here will be bounded by this constant, which doesn't really depend on anything, in particular not on Z. On the other hand, inside this circle, of course, we have a continuous function on a compact set, which will then also will be bounded there. So by combining these two, you see that this function will be bounded in the whole plane, and hence by Liouville's theorem it will be a constant. So this is the proof of the fundamental theorem of algebra. So let me end this lecture with one more consequence here now of the Cauchy integral theorem, integral formula. You can apply, suppose now we apply the integral formula to at a certain point and to the circle here now with radius r around that point. So that's what we call CR here now. And then we have f of w divided by w minus z naught dw then. Now you can actually express this integral by parametrizing this curve CR. You can just say that you parameterize it by letting w be equal to z naught plus r times e to the I t, where t goes from 0 to 2 pi. And this parameterization then gives you the formula stating that f of z naught will be equal to, well, first you get 1 over 2 pi I. But once you compute dw, you see that you get an I from there also, so the I will cancel out here now. And then you simply get an integral of this form here now, from 0 to 2 pi of f of z naught plus r times e to the I t, and then you get dt, because this e to the I t will cancel out against the denominator. So what does this formula here now tell you? Well, this formula tells you that any analytic function at any point z naught will actually be equal to the integral mean value of the values of the function along any circle with center at that point. So of course this circle must be in a domain where the function is analytic, but with only that restriction you see that the function will always be the mean value of its values on such a circle with center at z naught. So this is called the the mean value property of analytic functions. And this mean value property also has as a consequence something which is a very important property, which is called the maximum principle for analytic functions. So the maximum principle says that the maximum of an analytic function is always assumed at the boundary. Well, or it's not assumed in the interior, you might say, unless the function is constant. So the maximum of the absolute value of f of z can not be assumed in the interior unless then the function is constant. And well, the proof takes some technical details and I won't go through it now, but basically it's just a more or less obvious consequence of this mean value property, because what the mean value property says is that the function is at any point is the mean value of the values it takes on a circle surrounding that point. And this of course means that if there is some point on this circle where the function is less, the absolute value of the function is less than the value at the point itself, then at some other point the value must be larger. It couldn't be that the function is really larger at the center than at all the points on the circumference if this mean value property is true. So that's sort of the intuitive reason behind the mean value property.